state will say, yes, we've taken on board your submission and we accept it as follows, and then they'll publish it into some sort of a list. There'll also be a letter, and there'll also generally be some celebration. So the list, what does the list look like? We all have slightly different lists. We use a PDF list in Victoria. But generally, it's some sort of a list, often split up by different categories. So whether it's permanent products, temporary products, or legacy. In our case, and very similar to RMS and Queensland, that list will link to the recommended conditions of use. Now, in Victoria, we've slightly modified in the last, I guess, 3 months. We will now use the Austroads TCUs directly if we have no other conditions that we want to add. And the idea being that, we want to try and, promote that national harmonization. If we don't have any conditions, then we will adopt that directly. If we do have additional conditions, or we are accepting a product that hasn't gone through ASBAT, which would be very, very rare, we will provide some additional notes and or a link to the detail sheets. But either way, there will be a document that supports each of the accepted barrier products. RMS, they go with a website format. So I know that's quite small, but they've split it up by permanent, work zone, crash cushions, gates. Again, a general list of products, and each of these product names will have a link, and that goes straight to the TCU. So you always have the latest conditions in which it's been accepted. Again, they put the New South Wales, the RMS link on it, but it's very much the same format. So it's about trying to provide consistency for the users across states. Summary, I guess, of this, there is a bit to it. The suppliers do go through a lot of testing, a lot of evaluation, a lot of failure also occurs during that process. It doesn't always come out and succeed, and that creates learnings. And so I guess the one takeaway from this is that, don't use a product unless it's on the list. It just, we don't know how that works, or we don't know how it works in that configuration or in that scenario. And it just adds a risk. These products are in there purely to save someone's life. And so we really need to make sure they've gone through that duty of care, which is through the ASBAT assessment and through the State Road Authority's acceptance process. Always check the latest product list. Don't modify. So modifications, can be completely different products. They perform differently. So it might look like a small change, but that might actually be a critical element in the process. I guess just another thing that the state road authorities always have the ability to remove products from the list if they've been deemed, not working in field, or there's been a risk or an issue. Just because it gets through doesn't mean that's it for life. They're constantly being reviewed. Alrighty, so that is the first one. And I actually did that very fast, but that's good. Saves us some time for the various products, which is good.
Yeah. Well done, Evan. Well, you jump on to the next one. I'll just remind people to pop questions in as Evan's presenting into the chat, and I'll feed them to him at different points. I will jump back in with some questions a little bit later, but I'll let Evan continue on. No questions in at the moment. Evan?
No worries. Good. Either I was way too fast, or either I covered it well. We'll never know. Alrighty. So I'll get back to this. Barrier performance requirements. So really in this slide, or not this slide, but this presentation, I want to go through what we're looking at during that assessment. Where we subject this product to a whole lot of conditions and requirements, and the idea is that we hope that it performs out on site. And so what we are looking for, is what I'll talk about in the next 20 minutes. Testing. This is a very old video. I actually don't know. It was passed down. We had it on our system. But, you know, the first variations of safety barriers went through the same thing. Rolled a vehicle down a hill. It might not be as sophisticated as we have now, but the idea was still the same. Does the barrier or does the product redirect a vehicle, or does it perform the way that we want? Now, yes, that looks primitive. It's just a vehicle rolling down the hill, but it actually has the three key things that we still decide about today. What vehicle do you roll down the hill, or what vehicle do you use to impact the barrier? The second one, what speed do we use? What speed do we impact the barrier at, and at what angle? Now that looks very primitive, but they've actually covered off all of those. They've chosen a speed, they've chosen a vehicle, and the way they've set up the barrier, they've chosen an angle to test. And it's all about those three things. That's what's changed a lot over the last many years with testing. Yes, there's a whole lot of other detail in the how it performs and what's successful and everything, but those are the main differences between testing. First protocol came out in 1962, and over the years it's gotten more detailed about what to look for, what to test for, and those three things have changed. The vehicle type, the speed, and the angle has changed over the years. The most common ones that you may have heard of is NCHRP 350. So this protocol came out in 1993, about the time we were having a big boom of products being tested and developed in America. So a lot of our products have been rated to NCHRP 350. And obviously, as we can see, moving into 2009 and 16, MASH, the Manual for Assessing Safety Hardware. So there's two versions of this. There was some minor updates in the latest 2016, but this is now the latest standard. We have only been assessing products to MASH for almost the last 2 years now. And a lot of the states have just finished their transition in the fact that they have made a lot of these products legacy and now only accept products that have been tested to MASH. And we went through a big journey of telling all the suppliers we would be phasing out these products. We've given them 5+ years to start developing and testing, and we've really hit that point. Temporary barriers is really the only one to not occur yet, but down in Victoria, all permanent products must be MASH. Starting from the beginning of this year, we clicked over to wire rope, which was the final product type.
Evan, just quickly there, you used a term legacy. Do you want to explain that?
Yeah, so I guess legacy is just products that we have accepted and have installed, and they're out on our network, and we would call those legacy products, products that once were accepted. However, we don't automatically rip products out of the network just because we've moved to a new standard. These barriers are designed for a 25-year design life, and so often when we've removed a product acceptance, it'll be out on the network and we'll continue to maintain it for that 25 years because that's how much we bargained on when we first decided to install it. So we often refer to those as legacy products that may be out there on the network that we may be we may be maintaining, but we're no longer installing anymore.
Okay, thank you.
So back to the protocols, what brings these all together? And it's the Australian standards. So AS/NZS 3845 road safety barriers. Oh, it's road safety hardware, I can't remember. But AS 3845, and this is the Australian standard that brings all of these together. It basically says that we accept, or we only accept products that have been tested or have demonstrated performance in accordance with these three protocols. MASH has been called out as the reference, as the baseline, but we do acknowledge these other two standards. Now, the reason for doing that is because a lot of the development, the ideas, the funding from America and from Europe, they have the giant markets for for this sort of stuff. And so by acknowledging and using international standards, it means that we get all those latest innovations, all those new products that have been developed overseas. They can be simply brought to Australia, and hopefully all the testing they've done and all the evaluation will be, easily modified and adjusted for AS3845. Rather than developing a completely separate protocol, it's far more advantageous to us to adopt those protocols. But AS3845, that is the one that brings them together. And just a few notes around what I've just kind of mentioned. MASH is the basis. The other two protocols can be considered. And it also just a reminder that, products in Australia need to be assessed and, deemed acceptable in accordance with this standard. Just because it's accepted overseas by FHWA or by somewhere in Europe, doesn't mean that they've deemed it acceptable in accordance with our standards. So yes, the testing might be the same, but it is not a simple, yes in America means yes here. It still needs to go through an assessment process. Righty, why do we crash test? And the idea really is to understand a reasonable level of performance. Now, that doesn't cover the worst scenario. It covers what we call the worst practical case. If we were to line up all of the possible run-off road scenarios, from worst or from least worst to worst, we don't take the worst and test that. We look at how many of each of the different types, and we come up with a matrix of tests that tries to cover all of these scenarios. And generally that term of the 85th percentile or 90th percentile, we're trying to cover for the worst practical case. That limit where we start to get, the real value for money. Everything beyond that, can be harder and harder to try and cater for because it's more and more extreme. So we do test for a worst practical case. And I guess the other value of it is setting a bench line, setting something for people to aim for when they're developing products, but also gives us some consistency. We can understand how different products work when they've been tested the same way, and we can understand their pros and cons based on that. How do we crash test? So I talked about those three things before: what vehicle, what speed, and what angle. The first step, choose the vehicle that we're actually going to crash test. Now, this is a bit of a diagram up here that I captured from our registered vehicles database. This is the amount of vehicles registered and their weight. So you can see that the vast majority of all vehicles registered, and there was 4.6 million, and we're sort of getting a peak of just this vehicle. There's 1.4 million of them registered. That is the bulk of our vehicles. From then on, yes, we do have heavy vehicles throughout the network, and some routes will have more heavy vehicles than others. But again, it's highlighting that that's the key. And because of that, the two vehicles that are critical in every single test matrix or test level is the small car, which comes up around here, and the large passenger car, which comes up around here. So 1100 and 2.27. The idea being that these represent the 95th percentile of passenger vehicles. And to test with both of those, we're hoping to cover sort of that middle. And there are some specific elements around those that try to do that. For optional testing, larger vehicle testing, we then move sort of up all the way to 10 ton and up to 36 ton. And we divide those up by test level, and I'll go into that a bit in a minute. Here is a photo of the small car. I won't dwell on that. Generally with the small car, we're looking at underrun. The bumper is quite low. The shape of the vehicle is quite low. There's a lot of risk placed on the occupant because it's more likely to be thrown around during an impact. And so what we're mainly testing for is underrun. Does the vehicle get under the barrier? And secondly, does the occupant survive, and is there enough of a deformation that would be unacceptable? So again, sort of making sure we check for that underrun. The next vehicle, the large passenger vehicle, 2.27, we can see a slight change. That's actually the old NCHRP vehicle, and this is the new MASH vehicle. So they did change, they did decide to actually increase the weight of the vehicle and obviously the size and bumper, because that's what people were buying. This is what people were buying back in 1993. Now this is around 2006 and 2016. For this one, it's that big impact energy. You know, does it breach through the barrier? Does the barrier have enough strength, enough, I guess, ability to redirect that vehicle? And in how much room do you actually need? So this one generally has the most energy, the most potential to go over the barrier, as compared to the small car. So we are, both should be redirected, but we do look for slightly different things when we assess them. And then for the larger vehicles, which are optional, the small car and the small and large passenger car have to be done every time. Optional is these larger vehicles. Test level 4 uses a 10-ton truck, and test level 5 and test level 6 use a 36-ton truck. And I've got a summary of that in the next slide, and I'll stop on the next slide and go through it. For the trucks, again, looking for overriding. Is the barrier tall enough to actually redirect and capture the vehicle? And what's the roll? Often when you have a very short or rigid barrier, there's a lot of force placed on the truck to roll, and you will need a certain height to be able to stop larger vehicles. And that's why we look at concrete barriers. The higher they get, the larger the vehicle they can contain. The other option is to have deflection. The more deflection you have, if you allow the barrier to move, then the truck will remain fairly stable during an impact. And it means that you can actually redirect that vehicle and keep the vehicle more upright, but you will need room versus having a really tall barrier and trying to sort of stop that vehicle from rolling over. So this matrix is I guess, a summary of what I've been through there. And what we do and what MASH does is we split up the testing into various test levels. Test level 1, 2, 3, 4, and 5. And basically the higher the number, the harder it is to actually pass, and generally there's much more energy involved. Test level 1, often we have, not many products are only tested to test level 1. But to pass this, or to test level 1, the small and large passenger car, both at 25 degrees at 50 k's an hour. If we move up to test level 2, it's almost a double in energy. The small and large passenger car, 25 degrees at 70 k's an hour. And we do that once again for 100 k's an hour, test level 3. Test level 3 is the most common. That's where suppliers are aiming for, because if they can get that, then their product can be used on most roads, all the way, highways and local roads. If they only test to a small test level, like 1 or 2, then they can only be used on roads up to 50 and 70. So TL3 is the most common. Beyond that, TL4 and 5, we use the exact same small passenger car and large passenger car. We run them at 100, but we also add in the 10-ton truck and 15 degrees at 90 k's an hour. And for test level 5, we add in the 36-ton truck at 15 degrees and 80 k's an hour. Now, why install one product versus the other? Why not always install TL5? Because it stops the largest vehicle. And the reality is, it's about value for money, about getting the maximum benefit and reduction of risk across your network. TL5 barriers, like I'm showing down here, the only options are really concrete, 1.1 meters high. They are fairly significant barriers, and we do need those in certain applications, either a high risk of an asset or a high risk or consequence if someone ran off the road, or there just might be that amount of large or heavy vehicles. But to install TL5 everywhere means that we're just not getting the value for money on each road. And if we have a certain amount of resources, which we all do, we would be running out of money and running out of and leaving a lot more of the roadside unprotected if we went with TL5 everywhere. So the typical default is somewhere around TL3 or 4, and then only going up if there is a higher risk, higher consequence, a higher, a need to add that extra containment. And the only reason we'd be going down from TL3 is if there is that speed reduction and there's no high consequence. So you might still have a 60K road and there's, a good reason to choose a TL3 product. Which brings me, I guess, to the last point on this slide. This matrix of tests, so 1, 2, and 3, or 1, 2, and 3, are designed to test the performance. They don't limit the installation of these products to 80 or 90. They are used to define a test level. And it's around this test level that we believe TL5 products are suitable on high-speed roads, just like we believe TL3 are suitable on high-speed roads. The fact that they were tested at different speeds is really just the collective risk. It just so happens that larger vehicles generally run off at lower speeds and generally run off, at lower angles, and generally run off at lower speeds. So again, just to highlight that collectively, this makes up a TL5. It doesn't limit the need or your ability to use it on an 80K or 90K road.
A couple of questions, Evan. First one is any test for like a road train or if you were having really large vehicles, what would be the process there?
Yep. So when it comes to those larger vehicles, and I guess the only real experience for those is when we dive into the bridge space. They have standards for designing for 44-ton trucks and designing for, I think, even special. The way to do that, because it just comes really difficult just in a practical sense to actually run such a large vehicle into a barrier and see how it works. In those cases, it is really about just what is the energy, how does that energy transfer through the barrier and through the concrete and into the foundation. So we do have barriers that take really, really large impacts, but they've been designed rather than crash tested. The other thing is that you design for, you pick a vehicle, let's say a road train. What's important is to understand what is the angle and what is the speed that vehicle might actually come off at. It's easy to pick the road train, but if you also add on 25 degrees and you also add on 100 Ks, then it's just going to be such an impossible, impact to really contain. The truth is that lots of these barriers will take, this TL3 barrier might actually withstand or redirect this 10-ton truck or this 36-ton truck if the angle and the speed is such that the energy is similar. And so, no, there isn't any products for these road trains. I would suspect that some of the products that we have out there might still redirect a large vehicle if the angle and the speed is right out on site. But no, there just hasn't been any physical crash testing of such large vehicles.
Okay, thanks. And the next one is, if a product passes a test level, is it deemed then to have passed any test level below it?
So what we would say is if a product has been tested to test level 3 and it's been accepted, then that comes with a TCU, a length, a working width, a foundation. Now, that configuration, that barrier that was submitted as a TL3, yes, can be used for 100 Ks and any speed below it. And so, similarly, I guess if you tested to TL4, it can be used for it. That product that achieved TL4 will also achieve TL3, 2, and 1. So yes, but generally, I guess what I'm trying to say is that the configuration doesn't change. There's still going to be a working width and a length and a foundation that's all associated to the TL4 configuration and product. But yeah, you could use the TL4 product anywhere you needed these lower ones. Good.
Thank you. Keep the questions coming in, everybody, and Evan will keep moving forward.
Yep, no worries. A bit about energy. I did have energy on the other side, but again, just kind of showing that gradual increase in energy. The bit that I like to just point out here is the difference between the old NCHRP 350 and the MASH protocols when we talk about TL4. So you can see the gradual increase. All of the MASH ones are slightly higher than the 350, except when it comes to TL4. And there is actually quite a big difference. The old TL4 had the same energy as TL3. And really the main focus is the barrier high enough? Does it stop stop the vehicle from rolling over? Whereas under MASH, both the speed has gone up and the vehicle weight, which actually means these products are very, very different. If you're asking for a TL3 product, then there's going to be a subtle difference between the two protocols. Whereas if you're asking or need a TL4, there will be a big difference between NCHRP products that were TL4 and MASH products that are considered TL4. So just to note that big difference, especially when you're sort of comparing or your road authority accepts both types. So that was longitudinal barriers. Terminals is a whole nother story. Similar concepts, small and large passenger car, certain angles, certain speeds, and we can obviously see here sort of head on at an angle, but it also introduces a couple of interesting ones, which is the critical impact point. Test 34 is all about understanding the worst scenario, and the supplier has to actually convince us that they've decided on the worst point along the barrier and then tested it. Test 35 talks about the first point, the beginning length of need. So the first point that the barrier becomes redirective. Again, the supplier gets to choose that or guess that, and then they have to test it to prove it. And this last one here is the reverse angle. So imagine there is a longitudinal barrier coming in here. It's when impacting from the opposite side of the road or in the reverse direction. Is there any pocketing? Is there any risk or any transfer of energy into the driver? So, yep, terminals, same crash testing. Theory is there, but just more of them. Same with crash cushions. So a couple of extra ones because these are redirective from the nose. We actually do the small and large car at the nose. So there is that extra one, but same critical impact point and the reverse direction. Generally, you wouldn't do the reverse direction here actually on the crash cushion. You would do it here in that transition point, the point where you're going from this barrier to the other one. Because that's normally the critical impact point, the spot where there's going to be the highest risk of pocketing to the driver. Alrighty, so that's how many tests and the different types of tests you have to do. But each one of those tests has a criteria for evaluating pass or fail. And it's generally divided into three things. So structural adequacy, did the barrier actually stand up? Did it take the energy? Did it redirect the vehicle? And did it avoid or stop any overriding or underriding or penetration of the barrier? So that is all about, did the barrier survive and do its job? The second one, did the occupant actually survive during the impact? Obviously, we can pass, we can have products that stop the vehicle from traveling any further, but we also need to make sure that they don't injure or kill the occupant inside. Now, there's two elements, I think, that we looked at in there, both the deceleration, I guess, G-forces on the occupant, how do they go during an impact, but also did anything enter the occupant compartment? Was there debris that came through the window? Was there deformation of the compartment? There needs to be, only a very minimal, and it's spelt out in MASH, a couple of mils that's allowed to deform, but pretty much, the occupant compartment and the occupants need to be proven to be able to live. And the second one, or the third, not the second one, the third one, sorry, post-impact response. So where does the vehicle go after it hits the barrier? There is a preferred trajectory, and I will actually get into that in a diagram, so I might just keep moving. Structural adequacy, we're looking for tears and we're looking for scenarios where the product didn't hold up. If a product is right on the verge of failing, then it will get marked down, because when, we do want that extra capacity. So, we want it to be able to redirect the vehicle and still have a bit of capacity in it. We don't want it to be all designed right on the bare minimum. The occupant risk element, I'll just play this video, there's several elements in there. Does the vehicle remain upright? Did any elements detach and enter the compartment, which is actually this one up here, sorry. But also just the G forces. What is the occupant experiencing during the impact? And basically, these cars are set up with a whole lot of measuring devices that go in there that do measure this. There isn't specifically a dummy, though some do put in a dummy just to observe the behavior. But it is all about sort of that G forces and the impacts that are measured through the devices in the vehicle. I guess one thing I want, go, Ken.
Oh, it was a question that actually goes back a little bit. Sorry to take you back a bit. It was in relation to the half MV squared for energy. Is that taking into account anything associated with the vehicle? So the example being used is potentially like a B double or something where there might be some crumpling of the cabin or the trailers or these sorts of things.
The energy calculation, that half MV squared, doesn't actually factor into the testing. It's really just a good way to understand how much energy is in each of the test levels. The reality is that America have done an evaluation of vehicles that left their road, 4,000 scenarios, and they've measured the type of vehicles that left the road, the speeds they left the road, and the angles they left the road. So the scenarios that we test are based around those worst practical cases, based on data. Once you've set that, yes, you can do a half MV squared. That's how much energy the vehicle has when it impacts the barrier, and it gives us a good way to see how different the energies are and how much they increase. But it's not going into that level of detail. If you're designing the barrier to take that energy, which we do with bridge barriers, it's a whole different story. It's about how does the barrier actually take the load, whereas the failure points and the shearing. And so that would be the place that takes all of that. Given how complex that is for, wire rope and systems that deflect, that's why we test. because we just don't have the confidence that we really understand how that energy gets dissipated without actually going out and testing it.
Thank you.
So no, thanks for the question. That's fine that it went back. Just back on occupant risk, one thing I just like to highlight here is with the occupant risk, we get a maximum and a preferred threshold for each of the elements. Impact velocity, so when the driver potentially hits the steering wheel or you sort of moves forward during a sort of jolt, and then also how quickly the occupant slows down that deceleration rate. There is a maximum limit and a preferred limit for both. When we talk about each of the different systems, yes, they do perform differently. Yes, permanent concrete barriers do have a higher impact velocity and deceleration than wire rope, for example, but they're still far below the sort of maximum preferred. Yes, this helps us confirm wire rope is the most flexible and most forgiving system because these values are the lowest. Flexible guard fence quite close to that, and then there's a whole lot of guard fence and thri-beam and everything else in between. But I also plucked out the permanent concrete, which is still quite low when we're talking about 5 to 6 out of 9 to 12 and 12 to 14 out of 15 to 20. So these are all still very acceptable products. They both have their pros and cons, and yes, that's one of them. One of the benefits for wire rope and negatives for concrete. But, from this, very unreasonable to say something like a concrete barrier is unsafe system or unsafe or anything, because they still pass the same tests within the same protocols. Finally, post-impact response. Essentially, the crash test house has a whole lot of videos. One of them is an overhead video, and they make sure that the vehicle leaves the barrier and departs through this exit box and eventually comes to a stop. We don't want vehicles running off at high angles. They are required to sort of come through this section of the box. The challenge to this is that this is a test scenario. The vehicle goes in, no one is touching the steering wheel. The vehicle will automatically brake 2 seconds after. So generally they're leaving the barrier and then they're braking all the way up here. In reality, we do see this quite a lot, but we also see scenarios where the driver, has knocked the barrier there, turning the steering wheel hard to the right. And so they're intervening and modifying that trajectory. And we do see sort of vehicles leaving at high angles, on site. But I guess just to highlight that they're all crash tested to the same requirements. They all have the same performance and they all do leave in the exit box. Otherwise, it would be considered a fail. Okay, so those are the same videos that we saw before, but this one's a bit better down here. Again, just as you see the vehicle come in, looking for structural adequacy. Does the barrier remain intact? Yes, it does. Vehicle occupant decelerations are being measured, and we can see the vehicle sort of leave in that exit box area. Alrighty. All of this, everything we see during these crash testing and submissions get, I guess, added into this TCU. And I know that is a bit small, but the things that we look for in all of this is what test level that product was deemed to pass. Was it MASH TL4 or MASH TL3? What was the point of need that we saw for the terminals? What's the minimum length that we saw? What's the post spacing? What's the deflection? What's the working width? So we try to capture all the details about, what that barrier needs to achieve MASH TL3 or 4. The deflection and working widths could be new terms, but essentially these are how much room the product needs to redirect the vehicle. So in this case, I actually don't know what product I took here, but In this case, to stop a MASH TL4 or to provide MASH TL4 containment, you would need 2.46 meters behind the barrier, behind the face of the barrier, to contain the vehicle, any roll of the vehicle, any deflection of the barrier itself. Obviously, these numbers are smaller as you go down in test level because there's less energy, the vehicle is smaller, there's less roll. But yeah, we try to capture all of these conditions, what terminals are accepted, any additional factors that came in, and what pavement conditions. In this case, it's just a driven post, so it is suitable for a whole lot of different pavement types, but some aren't. If they're pinned to the surface, then there needs to be a strong enough surface. If they have a foundation that relies on soil, then they might only be suitable for that. So the TCU is really your key document for how to achieve the test levels and how to install that product correctly.
And you will all be getting some practice doing that in your assignment this week, which is you're all given a specific barrier type, a proprietary product or a public domain system, and you've got to go find that TCU and find some information about it for your jurisdiction. So if you're a little confused at the moment, it's always much better to go through the process and then it'll start to become clear.
Yep.
Now, there's no immediate questions that have popped up. So while you change over the slides, Evan, I'm going to put a little poll up, a little question on some of the stuff that you've, 2 questions actually. And remember, people, you're not being marked on this one, but the quiz at the end, you're actually being marked on. So this one's just a little bit of practice for you on a couple of things. 2 questions there. Also give you a minute or 2 to have a stretch and fill up your water after you've done that. So we're going to come back in 3 minutes. But the 2 questions are, what does TCU stand for? And ASBAP approves barriers. True or false? A little bit of a check who was listening intently there, Evan, no doubt.
Yep. It is the question with road trains. It's Bruce Snook's obviously on the panel, and we talk about that quite regularly. And it is a challenge, and it is a challenge, I guess, for especially in Western Australia, to choose the best test level. What is the optimal test level that gets the most value for money? Because there's such long lengths, and some of the vehicles are really large. And okay, choosing TL5 or 6, might be able to stop those vehicles, but are you getting the right value for money and benefit for cost? That is the tough thing. And so it's really important, I think, to sort of decide up front, what is the test level that we need here? Because it makes product selection and product and design so much easier, because you're designing around a test level and trying to achieve that test level. If you leave that blank, then it can get very tough in choosing a barrier and then saying, well, how on earth am I going to make this barrier be able to redirect a truck or a road train, which is just almost an impossible task. So it is about setting that test level up front, so that you know that you're working towards a reasonable and practical test level.
Has anybody, just while we get our last few in there, Are you aware of anybody doing some thinking around multiple barrier systems running longitudinally? I know for, I suppose, I think gantries, there's some advice that you would do that, but in more substantial...
Not really, no, other than that exact scenario. So having, for example, the flexible system up front, so that captures your passenger vehicles, whether that's a wire rope or a guard fence, and then having a more rigid, higher containment barrier just around the high risk locations, whether that was a school or a bridge or a bridge pier. That's about it. And we still only design them to interact or to be independent of each other. So there's no real work going around about what if we put them right next to each other, how do they interact? Or there's nothing being done around does 2 TL3 barriers make a TL4 or anything, which was definitely a conversation at one point on one of our major highways is, if we put 2 rows of TL4 concrete barrier, is that enough, or do we need to upgrade to TL5 or 6? But no, I mean, you could simulate it using some of the more advanced models out there, but no, nothing that I've seen, and nothing that I've really seen coming out of America or anything.
Yeah, okay. Oh, that's fascinating though. All right, thank you. I'm going to end that poll now. We almost got everybody in there to answer, but there you go, displaying the answers to everybody. TCU, so a couple in there to try to fool you with barrier terminology, but technical conditions of use is the correct one. I managed to catch a few people there, but those are, as Evan mentioned, the sheet that you'll be looking at. And ASBAP approves barriers. Well, most of you are right there. That's false. ASBAP recommends, is that correct, Evan? Recommends barriers, and then the authorities decide what they will approve.
And I would say ASBAP assesses barriers, and then ASBAP recommends barriers, as per that assessment. But it is the road authority that gives that final approval to use them.
Yeah. And we did have a question come in, which I'm actually going to make into a prize-winning question here. Somebody's just wanting to recap on what ASBAP is and it stands for. So the person who can type in what ASBAP stands for, the acronym ASBAP first, I will add you to the prize pool for this week. Ooh. It's people are trying to go in there fast, and we got very close. I think I want to give it to Steve. I think it is. I got to stretch my screen out to see. I'm going to give it to Steve. Got there sort of in the end with 2 barriers, but the so the Austroads Safety Barrier Assessment Panel. So Austroads being the sort of the body of, I was going to say governing body, but it's not quite right. Overarching body for road authorities for Australia and New Zealand. And there's a panel of people from the road authorities that do this sort of analysis and make those recommendations, I suppose. Yeah. So Steve, you win, and very closely there, followed by Catherine and a few others. Okay, thank you for that. Back to you, Evan, to continue on.
No worries. Righty, so this one, a bit longer than the others, but this one we're going to get into the various types of permanent safety barrier products. And so definitely this will help with the homework. Obviously, I won't get into the TCUs of each product. I won't get down into the nitty-gritty detail, but I just want to talk about the general types of products that we have out there, some of the pros and cons, just so that you can get a better understanding of how they work. I will skip the first few slides only because we sometimes do these not quite together, and so it's a bit of a rehash of where all the information is. But You should be familiar with this, the list. So I'm just going to work through our list of accepted safety barrier products for permanent now, and I'll do temporary after, and go through the various categories. And we generally break them up in stuff like flexible longitudinal, terminals, crash cushions, and then onto temporary barriers. So I'll go through the general types. The first thing I just wanted to quickly go through is this difference between proprietary product and public domain. A proprietary product is a barrier system that a company or an organization owns the intellectual property to. So they've gone away and developed something, they've invested the time and effort to test, and therefore they are the ones that you need to buy the product off. Now, the person with the intellectual property may actually be in America, but there'll always be a supplier, a barrier supplier down here in Victoria or in each of the states. They might manufacture components. They might get steel barrier from over there or these posts from over there, but there'll always be a proprietary supplier for those. For public domain, and there is less of those, the concept is that the barrier can be made by whomever. And examples of that are your G4 or your G9 or Type B for those in Victoria. We give you a standard drawing about how to manufacture them, what the requirements of the steel are, and basically, no one owns the IP of it. You can just go out and make it and install it. But we are definitely moving much more to the proprietary product space because they can put that business case together to invest in variations and adjustments and improvements. And so I'm not too sure that we'll go through too many public domain, but it is just a key terminology to note. Alrighty, so let's talk about the first product category, wire rope safety barrier. Wire rope barriers, whatever. Cable barriers, often referred to by America. They are pretty similar in what components they have. So they all have some form of a concrete foundation. The size and the depth might be slightly different, though most of them are the same, but they do all have a foundation. They will all have a post sleeve. So a plastic sleeve that gets pushed into the concrete and sits down inside the foundation. The shape might be slightly different, but they all do have a post sleeve. They all have posts, fairly self-explanatory. The shape might be slightly different, but they do all have steel posts and they will fit down within the post sleeve. They'll all have cables. In Victoria, we only accept 4-rope systems. So there used to be a couple of 3-rope systems back in the day. We only accept 4-rope now. It just gives a greater spread. It maximizes our chance of containing the larger vehicles and the smaller vehicles. And the extra cost of 1 rope was very negligible versus that benefit that it provided. So they all have ropes and they either feed through the barrier or around the barrier. The post, sorry. But either way, they are connected somehow to the post. And then they all have a terminal. Somehow the cable has to get from this height down, whether it's using a bunch of posts like this or a couple, and they are all anchored with a much larger anchor foundation. And these hold the cables in place during an impact. This is what it looks like in slow motion. The cables release from the post. Now, I might just hold it there. I might go again. The cables release from the post. They stay engaged with the barrier, with the vehicle. So you can see all of those cables engaged in there. And you can see that the cables are still connected and still running through the post. So the posts hold up the cables. Yes, they hold them at the right height so that the vehicle impacts and engages with the cables, but they also provide that resistance up and downstream. And you can see that as the vehicle deflects, it's pulling on these posts. These posts haven't actually been hit just yet, but they're pulling over when the energy is enough. Now, why that's important is because there's this misconception that all they do is hold up the cables, and therefore they could be made out of anything. Whereas that strength, that the way they hold the posts and the strength before they bend is super critical to the performance of the system. And in that respect, the more posts you have, the less the whole barrier will deflect, because there's more resistance, there's more force holding the cables in place. On the reverse, why not use a 9-meter post spacing? Well, there's just not enough posts holding, and the barrier will deflect a significant amount. And we also have the risk in really large post spacings of the cables going up and down. This scenario, there's lots of posts holding the cables together so that they engage with the vehicle. But when you have a really large post spacing, some of these cables can go up and down over the vehicle or under the vehicle, which is not a desirable outcome. So just to highlight that, the cables release from the posts, but the posts do provide a significant factor in how the system performs. There is 3 MASH wire rope systems: Bryphon, CenturyLine M, and the MASH Flex, each from the different suppliers: Safe Direction, ACP, and Ingel. The Ingel actually has a new post cap, so that you don't have to install all the spacers, whereas CenturyLine looks fairly similar to previously. The difference with each of the systems is kind of what heights the cables are, and I guess what post type, but the cables are pretty much identical. Each barrier has only one terminal, so there isn't really an item for what terminal you can use with it, because there's only one to be used. The Bryphon has the Bryphon terminal, CenturyLine, and MASH, so there is only one for each of the systems, and they've all only been accepted because there was a terminal. Benefits of why? Yep, go Ken.
Yep, sorry. Just questions come in. What is the liability or responsibility to replace an old system, like a 3-cable system? And sort of within that is another bit of a question around, if you're planning a job and you've sort of done work associated with an old system, when do you have to go back to the start and do your designs all again, or where does that line get drawn?
It is a good question, and I don't think I can answer it on behalf of your road authority. I can give you some guidance on, I guess, our approach in Victoria, and the reason why is because when these products were installed, they had a certain value, and they will last, and they will continue to provide that value for 25 years. It's very, very rare that we remove a product because it was failing. And the only real examples of that are sort of BCTAs, the old sort of terminals. And in that case, we said, if you're near one, replace it. But in the case of, I heard you say 3-rope wire rope, or potentially just an NCHRP wire rope, it's all about this extra value. We've said that 4-rope systems are more valuable than 3-rope. So when you're installing them, we found that you should only install 4 ropes, because that is an easy benefit. Now that we're moving to MASH do provide more value, more redirection and containment than 350. So new installation should be MASH, because that's an easy one. However, the benefit gain from upgrading a 3 to a 4 rope is not as much. Yes, the cost is less as well, but it's all around how much you're willing to pay for and what it's worthwhile. We actually did some work with our Safer Roads program around this, and we identified a whole lot of systems that were in that category. Some old W beams that were really low, 706 mils high, we said must replace. For some of the wire rope terminals that just weren't crash tested, they were really old terminals that were kind of just there because we needed them back in the day. I'm talking 15, 20 years ago. We said have to replace those. But for your 3 ropes, for your 350s, we've decided to leave them until there is that enough value in upgrading them for the cost. I know that was a bit long-winded, but I hope that does cover that question. So again, I guess just it's kind of up to the road authority to say you should or shouldn't.
I'm going to come with a follow-up on that and add temporary systems into that. So is there just a point where you just cannot use some of these older systems?
Yeah, temporary barriers. Yeah, good question. So what we've done with industry is give them time to change over to buy new products. And basically at the end of this year in Victoria, each of the states might have a slightly different date, though I know Queensland and RMS are the same. The end of this year is a date, and all, I guess, all projects signed after the end of this year will have to use MASH temporary products. Now that means your Coates Hire and your companies are buying them currently so that they can use and they can supply MASH temporary barriers on all projects starting next year. For projects currently going, you get the option of either 350 or MASH products, temporary barriers. If your project has been signed off and you're already using the temporary barriers and your project extends into next year and onwards, you can keep using those. You don't have to replace them mid-project. But I guess just to be aware that when your project ends and you start a new one, you're probably going to have to use MASH, especially if you're ending and starting a new project next year.
Good. Thank you.
That's all right. For South Australia and WA, I actually can't remember the dates, so it would be worth double checking their website. Alrighty, wire rope. Pros and cons. I won't go into all of them there, but your big ones are, it's the most forgiving system. We talked about the deceleration, the injury values to the occupants, they're the lowest. Wire rope also has a fairly high containment level. Test level 4, it has been proven to redirect and contain your large vehicles. And it even has that extra capacity. We've had cases where, very large vehicles have impacted the cable. Yes, it deflects more, but the cables have a lot of capacity in them before they would ever snap. So, wire rope does have quite a good containment level. However, limitations are you'll need a deflection zone. You'll need a fairly large deflection zone. They don't work around tight curves. Because they're all pre-tensioned, it can, if it's a cold morning or day, they can actually, get really tight and pull over the post. So they can't be installed on tight curves. And look, the obvious one is they, don't have any attachments, any really effective attachments for motorcyclists. For roads where that risk to motorcyclists is low, straights, and we've got a good offset, they're great. There's no reason not to use them and to preference them. But where you do have sort of that known motorcycling risk, curvy, windy roads, frequented routes for recreational areas, there's no, really suitable, really effective solutions for wire rope, whereas there are for guard fence, which we'll get into. So flexible guard fence systems. Now, I know we've got a mixture of people around Australia. So that is a Victorian term, flexible guard fence. Another term is really just a weak post guardrail. The concept or the reason it is that is because the post does bend over just like the wire rope one does during an impact. The rail will release from the post and will stay engaged with the vehicle. So it's kind of a very similar performance as we saw in that video. The post will get out of the way, the rail will stay up against the vehicle, and the posts up and downstream, will provide that support. This one is, I guess, a little bit different because the cables can't spread and, go over and under the vehicle. It is one rail rather than 4 cables, but still works in a fairly similar way. We have a few flexible guard fence systems, and I'll focus over here on the right, this row of images. We've got a EasyGuard Smart or EasyGuard 4 MASH W-beam, a Ram Shield MASH W-beam, and a Sentry Barrier MASH W-beam. They all use exactly the same W-beam. It's the posts and it's the connection that's different. This connection is how it releases from the post, or how the W-beam releases from the post. And that is the real critical bit. It needs to hold long enough to engage with the vehicle and release, as needed so that it stays upright and doesn't go under the vehicle. I guess moving on from the W-beam systems, we do now have 2 Thri-beam systems. So you can see the W here is kind of sort of 2 humps, Thri-beam 3 humps. It's wider, it is taller, and so that's what you really need to get your MASH TL4s. It just has a lot more capacity, a lot more strength, especially for those larger vehicles with the larger energy. Are these both considered flexible guard fence systems? Yeah, questionable. They're both guard fence. They're both guardrail systems, W-beam and Thri-beam. The flexibility of them, yes, is different. These W-beam systems are more flexible than the Thri-beam systems. But again, it's all about containment. It's all about deflection, when you're choosing the right product. So let's have a look at these. Very similar to wire rope. You'll see the first couple of posts bend, they get out of the way. The rest are holding the W-beam, and the W-beam stays up and connected with the vehicle. So again, why it gets its name, weak post system. I think just a different angle. But again, we see it sort of engaged up against that vehicle, making sure that it doesn't go under or over the vehicle. So that interaction is really, really important. And it's often one of the things I focus on in constrained locations when we're talking about, can you have a batter and can you have a curb and can you have all these things in front of the barrier? That's the critical bit. Does the vehicle hit the barrier at the right spot so that, it can actually, engage, it can dig into the vehicle and it can redirect it. Once that vehicle is engaged, it can take a little bit of movement if it was, running over curb and stuff, but changing how it hits the barrier, can have a big difference on, how it actually performs. So not really for this session, but I just wanted to throw that out there. Guard fence just in general, whether it's flexible or normal, these are your less, you're more constrained. It's not your freeways where you have plenty of room with good offsets. It's the other scenarios. Whether it's a hazard that's close to the road, it's a windy road. This might be a motorcyclist friendly route. Well, hopefully it's not because there's no rub rail on it. Take that back. But again, just trying to show the difference that, this is not the sort of scenario that would be useful for a wire rope because you wouldn't be able to get around the curves. You don't have the offset or deflection room. So for guard fence products really fit well within these areas. It's still very forgiving, useful for tight curves. The other element here is no periodic maintenance. So the W-beam isn't pre-stressed. It's just a length of rail, which means that we don't have these fluctuations with temperature, and after an impact, the damage is really localized. So it's really just about checking if it's been hit and damaged Otherwise, it's a pretty much install and forget type scenario. The other benefit is the motorcycle rub rails. We do have accepted rails that can go underneath and protect the posts and the hazards behind. And these have only been tested and demonstrated to be suitable with guard fence type products. But a very big benefit of these. The main limitation, containment level isn't as large. W-beam will only achieve TL3. You'll need to go up to a Thri-beam to get TL4, which can be a bit more costly. And it can be a little bit harder to replace the posts. Obviously, with wire rope, the foundation, underneath the ground surface doesn't move. It's pull out the damaged post, put in a new one. With these, you will have to remove the whole post and install a new one. Sometimes, depending on the soil, that might mean there's a little bit of movement, especially if your soil is quite weak. Look, it's not a showstopper consideration, but it's just one of the limitations. We start to move into a bit more rigid, so still have deflection, but each of the posts are doing quite a decent job at taking the impact. They don't just bend and get out of the way. And in these categories, you've got your public domain systems. So I've got a G4 there, a Type B shown there, very similar looking. Both happen to have curve in front of them. We also have a couple of proprietary. So that's the T39. We also have the G9 in other states. And then all the way up to your roller barrier type products, which, yes, there's some deflection, but they are, quite solid, very good. And I guess I'll get into the reasons why. Low deflection. You can achieve TL3 or 4 with very little room to the hazard, which means you can get a bit more offset to the traffic lane. You don't need as much room. So suitable for constrained locations. The main limitation is they cost a bit more. In some cases, they can cost a lot more, but that may be worthwhile to the whole of life. And I sort of go back and give an example. We've got 2 installations of roller barrier here in Victoria. And yes, they did cost more than the typical guard fence that we could have used, but it's been much more resilient against the regular impacts. And we had them on some really tight curved off ramps. We just didn't have the funding available to realign, which would be the preferred option. We did need to treat it so that we could stop people from running off and into the hazards. The barrier there previously was getting hit and damaged all the time and required a lot of inspection and repair, whereas the roller barrier, could withstand those nuisance hits. Yes, it would deflect during a big impact, but for these sorts of scenarios, we're getting sort of a lot of benefit, and whole of life actually might be positive. Well, no, very likely to be positive. Alrighty. I just wanted to quickly touch on variants and modifications. Over time, a lot of these products are being tested or retested and simulated and explored so that we have options for constrained locations, options for underground services, and et cetera. These all go through the panel and they're generally listed on the TCU, whether it's base plates or post emission. But I just wanted to quickly go through a couple of fairly common ones. Your base plate variant, could be attached to a shallow concrete foundation. If you have a culvert underneath, or if you had a service underneath, it means that we can get the performance without having to go, sort of 1800 down. Post emission. So a couple of the suppliers are now testing with one big span to get over a pit or to get over a service. In this case, you simply take the post, move it in between the other 2 existing ones, and you do that twice. So you've sort of got 2 meter post spacing, 1 meter post spacing, and a gap, and then back to 1 meter post spacing, then 2. So again, very useful, and those variants will be listed on the TCU. Abraham blocks and Easy Lift are another couple of attachments that are either approved or not in your state, and that's to get the height of the barrier up, for either an asphalt overlay or in this case, because our old guard fence design was very, very low, and rather than ripping it out and reinstalling a brand new product, we worked on a new way of getting the height of the system up so we could contain those larger passenger vehicles. And this is the option that we have adopted for a while, probably less so now, to try and get that height up. But these would all be listed in the TCU if they are accepted. Alrighty, terminals. It did take a while. I might speed up a little bit. We've probably got 20 minutes for terminals, and then I'll get into 20 minutes of temporary barriers. As I mentioned, only one wire rope terminal per wire rope system. So you can't really mix and match. You just have to follow the drawings or the manual and install what you get. These are the older 350 products. They kind of look similar in the new MASH products, but essentially trying to get the height down to an anchor block. Yes, these have been fully crash tested. I guess the one downside of wire rope terminals is that they're not absorbing too much energy. They've passed all the tests, the vehicle will ride up, come back down, the posts will knock out of the way so that it stabilizes, but there's still a lot of energy in the vehicle. And so I guess, if you have to place a terminal really close to the road or on a curve or something like that, then, you might choose that wire rope's not the most suitable just because of the terminal. So yes, terminals can have a big factor on which is the most suitable. If I needed to stop and start a barrier quite often, I would also cater or factor in, how good is the terminal? Is this the most suitable terminal? But yeah, just a reminder that there's only one per system. For great terminals, generally there is one terminal for each proprietary guard fence. So we've got MSKT for Ram Shield, ETSS for Easy Guard, Max Tension for Sentry Barrier. Because the supplier just wants to give you one product, they generally just say, mine's the only terminal that goes with my barrier. For public domain, so for your G4 and your Type B, all of these terminals can be used. I guess one of the values, and kind of conversely to the wire rope, is they do absorb energy. So they will bring a vehicle to a stop or to a much lower speed. And I'll go through that in a moment. No, nothing else. General stuff. Typical length is about 16 meters, tested to 100. Not going to go into this detail because that's all in the TCU. You can pull up the TCU and see all this information. What I do want to talk about, though, is how these systems work. And one, I think it's interesting, but also it's useful to identify, what are the key components of these terminals? How do they work? What am I looking out for during installation? There are two types, an extruder system and a tension system. And I'll just go back a minute. This up here is the extruder system. And you can actually see there's no cables or there's nothing running down here in the front. And I'll explain why in a minute. These two systems are called tension systems. And you can see actually a cable coming down in front and being anchored, and similar again over here on the ETSS. Now in the first one, it's essentially, I've got the W-beam lined up here, and it's essentially a steel head placed over the top of the first rail. Not necessarily connected together, but rather just placed over the top, and there's a post here to keep it in place. When someone comes on, an errant vehicle hits the end of that terminal, that head pushes the rail through a small chute. And obviously, as we push down, the system gets pushed through this terminal head, and that's how it absorbs energy, through friction. As the system sort of moves down, friction is being absorbed and so is the energy. And by the time you sort of get to that 16 meters, you've absorbed enough energy to pass the test. That's what one looks like after it's been hit, you know, with a fair amount of energy. It's been able to push that much rail through the head of the system. I do have a video next, but I'll get to that. Obviously, the most important thing about this system is getting that terminal head on top of the rail. You know, if this was somehow sitting outside, then when it's impacted, it won't feed through, and that can be really, really bad. So the biggest thing you can do, which, you know, if you install it per the manual, then that's fine. But I guess the biggest thing to note is merely making sure that that terminal head is on top and is sort of overlapping with that W-beam. The second type, the tension type, slightly different. We looks fairly similar from the surface, but they've got this post up front that's ahead of the head that anchors either a cable or anchors some form of a steel rail or cable. When the terminal gets hit, these W-beams sort of concertina over each other, and this cable gets pulled along, and there's sort of almost a grip or a clutch on here. And as the system gets pulled along that cable, it's absorbing energy through friction. So again, the most important thing is making sure that that is anchored so that when it's hit, it doesn't just pull the whole cable out and you know, sort of run along without any energy absorption. And the second thing is to make sure that, you know, this friction point is fully engaged. That used to mean turning a component so that you had the lock on, which was really important, because if you left it open, then there was no friction. In some of these new systems, they've made it really foolproof in the fact that you don't even have to lock something. If you put all the components in the right spot, it's automatically locked. So making things much easier for MASH, really then you're kind of just making sure that it's actually installed right. So yeah, I just wanted to go into a bit of detail on that. Here is a video of the extruder head. As a small car comes through, you can see it being pushed out. There is a bit of rotation. You know, once enough energy has been absorbed, you know, once the speed has been reduced enough that it can no longer push through the head, then, you know, it'll generally stop and the vehicle may rotate or just come to a stop. So again, just to sort of put that or show those principles in action, you know, the rail being thread through the terminal head. Next up, crash cushions. So you might see less of these around, often because they're a bit more expensive. Oh, maybe not even a bit, a lot more. But they are very, very good devices. You know, they're anchored to the ground, which means they're self-sufficient. They don't really rely on the barrier up and downstream. You can put them right on the end of a concrete barrier, right on the end of a hazard, whether that was a bridge pier or something else. So they are very, very good. Can be designed for greater speeds. So you can, you know, they're only sort of around 8 meters long for 100 Ks, but you could reduce that for lower speed and etc. So they are very good. And I hope this video kind of shows that. I know it's fast, but you know, that's a 100 kilometer per hour, 2-ton vehicle, and the occupant, you know, deceleration is, you know, well under, on an angle as well, a very controlled impact. Yes, you've got to absorb a lot of energy, so it's, you know, it's not going to be the most forgiving, but especially when you haven't got the room, you know, they are very, very good systems, though they do cost. And the sorts of locations we would use them in Victoria is on your off ramps or your highway gore areas, etc. And I've got a few photos about that later. Again, just with crash cushions, I just wanted to highlight the two subtly different ones. Several work on a cartridge type mechanism. So you've got a whole lot of steel placed together. The idea is that when you hit the end of it, these all sort of, crumple, but you've got these cartridges inside, and these cartridges will crush and absorb energy. The strength of each of these cartridges is what makes the system. If a cartridge is missing, then it's missing its strength and it's not going to absorb the amount of energy needed. The downside of this is that after an impact, all your cartridges need to be replaced because they're damaged. So cartridge systems rely on the cartridges, but you need to replace them. We also have another type, the smart terminal. Actually doesn't have cartridges. The actual crash cushion looks very similar in the fact that there's a whole lot of steel and sort of bays, but it runs on this hydraulic piston, which is connected to the front of the terminal. And as the terminal gets pushed along and the bays sort of crumple, the piston is what's taking all of the energy. And so, while this is more expensive, again, than the cartridge systems, you actually don't have to replace any cartridges. And so it is becoming fairly popular in Victoria, especially locations that might get hit, because it's really quick to fix, really quick to sort of reinstate, and not many components that are needed. Sorts of locations, exactly like this. This is a couple of urban areas, on a pier where you just don't have the length for a guard fence and a terminal. And also sort of on a freeway here, crash cushions on top or overlapping with the roller barrier. And I think there's one more again, on a concrete barrier on a gore section where there's one set of lanes are going to the right there and one set's going to the left. So you do need the product to be able to work from all angles, which is what we call a gore area. And in this case, they've used a variant that is flared or widened at the base. So crash cushions are very, very useful, though they do cost a little bit more. Short radius curves, I just wanted to, I guess, you really need to talk to your road authority, but wanted to touch on these. They're not published in the list of accepted safety barrier, terminals or treatments because, there's not too much testing around them. There has been, many years ago. However, they are still a necessary evil. They're, for hazards that are big drop-offs, really serious hazards, and we just don't have the room to run a barrier along the road because this might be a driveway or something, then they do provide a good wraparound treatment that will protect sort of someone leaving the road before they run off into this hazard. I guess the key to remember, though, is that they require this area for almost like a net. And so if your hazard is a giant drop-off or a river or something, then, you're probably going to have the room to provide this. But if you're thinking about using them for a pole or some other hazard that's in this area, well, you haven't really provided any protection because they do need that area to run off into. Transitions, each of the, if a product can be directly connected to another product, then there will be a transition. And it will generally say something like, transition as in accordance with this drawing or this manufacturer's manual. The general gist, though, is that, when you're going from a more flexible system, one that deflects more, into a more rigid system, you need to gradually stiffen. And, generally that might be additional posts, or you might move up to a thri-beam system. But the idea is to try and stop vehicles from pocketing or being redirected into the back of this more rigid system. So always keep an eye out for what transitions have been accepted. Normally, it's going to be, guard fence or thri-beam onto concrete. That's the most common transition. There are no wire rope transitions. You can't connect a wire rope to a concrete or a guard fence. The only way to change from one system to the other is to overlap them, to have two different systems overlapping. And here's an example of that. And this is sort of the transition that you will be seeing coming up shortly. There is an Austroads webinar on the 11th of Feb, which is open to everyone. I think you should be able to find it just by going to the Austroads website and MASH transition. And there should be something that pops up, and we'll talk through the new transition coming, which again is from guard fence into concrete. As for various other products like Raptors and Bollards, we do have a couple of these in our accepted list. Again, these are kind of they're necessary in certain applications, but they do not do the same job. They do not provide the same level of performance as longitudinal barriers and terminals that are being tested to MASH. But we do note that, in various cases, there is just not enough room to protect a pole, and something is better than nothing if you've got the room and the space. But also, in dining areas and etc., where we do need people to be walking through, a bollard can be better than running into the actual road users or the pedestrians. So products like this are on our list, but we have conditions around how you can use them. Rigid concrete barriers are, so all rigid concrete barriers are public domain, which means that there's no real off-the-shelf products. Some suppliers will make off-the-shelf precast units, but they've all been designed, and they should be designed to each of the state's requirements. And that's what I mean by public domain. Technically, any precaster could make them, or any slip former could make them, as long as they meet the road authority's requirements. Generally speaking, with concrete barriers, it's all about shape. In Victoria, we require it to be F shape. Not because it looks like an F, but because they tested A, B, C, D, E, and F. And the F shape, the last one, actually had the best performance for a small car. So we require it to be F shape. However, some other states do accept single slope. So it is a barrier of a single slope all the way down to the base, and that slope is a certain angle. I'm mainly talking about Queensland and South Australia, I think, are also adopting some single slope, but it's generally a mixture between F shape and single slope. The height is super important, as I talked about. To get the higher test levels, you will need a higher barrier. Reinforcement and anchorage, so the whole system needs to remain rigid during an impact. And you can do that by sort of connecting all the units together, embedding the system a certain depth so that it all acts as one massive concrete when impacted. But to do that, you need the right amount of reinforcement, the right connections, and the right anchorage. And that is essentially the requirements by the road authorities. What shape, what height, what reinforcement and anchorage do you need? A little shape there. New Jersey shape is slightly different to F shape. Yes, it looks the same, but it is different. And there you've got sort of the single slope barrier. I'm not sure if that's the angle that they use, but this is just the Texas single slope. Insulation, very, very important. Check your road authority's drawings or specifications on that. But yeah, the key to take away here is it needs to be anchored. It needs to remain rigid during an impact. As for bridge barriers, different story. Barriers that are attached to a structure, so either attached to a bridge deck or on a bridge or attached to a retaining wall, they might look the same, but they come under a whole different set of requirements. We have, design life that could be 50 to 100 years. We have durability, how it transfers the load into the deck. And so AS5100 is your key reference for any barriers on a structure. The testing of them is kind of similar in that they're meant to contain the same types of vehicles and impacts, but a TL4 wire rope does not constitute an AS5100 compliant barrier because it just doesn't have the design life. It doesn't transfer the loads in the way that AS5100 requires. So again, just to highlight that, and because of that reason, there are some subtle differences. This will be an AS5100 compliant product. Similarly, they're now using the F shape, but would be AS5100 compliant. And in cases like this, there's an aesthetic value of being able to see the landscape around you. And so they've modified that F shape to get the height, but also to allow that sort of permeability. Alrighty, I can see A1 up the top. Is that a question up there, Ken?
Yeah, sorry, Evan. I'm just clarifying that one question in the Q&A. There is another question in the chat there. Just who writes the actual technical conditions of use? Who writes that page?
Yeah, so the panel, when we do a pre-assessment, we are filling out and identifying the values that go into that. Now, that will be based on the values that the suppliers asked for. So they might ask for certain values and then say, here's how we're going to prove those values. So it's kind of written by the supplier to some extent. And then we'll adjust that if we disagree with what they've asked or they haven't provided enough evidence for something. The TCUs themselves are then written and published by ASBAP. So the coordinator and chair of ASBAP are the ones that actually do the physical typing. Though, we're all kind of looking at the same screen when they get developed. And then I guess for state-specific TCUs, so that, some states might recreate the TCUs. That's going to be the relevant area in that road authority. No doubt they'll use the TCUs that were written by ASBAP, but they might write them and add some additional information or put them in a new format. So it will kind of depend on which TCU you're looking at and who's actually provided it. But all the information comes from the suppliers.
Good. All right. Thank you. And there's a second question in there from NZ about the F profile barrier, but I need a bit more clarification on that question. I'm not sure I quite understand it. So,
yep.
Kick on with temporary. You got about 12 or 13 minutes on that, and then we'll wrap up.
No worries. Look, that does sound pretty quick, but I guess never really going into heaps of detail other than the different types of products. And I think I can sort of summarize those fairly well. First, just to say that temporary barriers are tested the same way of permanent products. They all have TCUs, they all have deflection areas and etc. So there are a lot of similarities between everything I've just explained around product acceptance, performance, and the TCUs. It's really just the actual types, of which there are four. Generally a concrete type, a steel type, so fully steel, a composite, so a mixture of steel and concrete, and then water-filled. I'll go into those. Concrete, probably seeing them all around. The only real difference between these is how they're connected together, other than the supplier. The connection is important though. The more it can move, the more the system will bend and deflect during an impact. However, the less it can move, the harder it is to go around curves. And so there is this real balance of, how tight do you make the connection? One, you get the best deflection of all the systems, but two, you can't actually use it on curves. And so again, that's the kind of subtle difference between them. Steel products, very similar in how they behave. I guess the big difference to concrete is concrete has a mass. They're quite heavy, and when they sit on the surface of the road, they have enough weight to sort of connect together and mass to redirect the vehicle. In the case of steel, there's not weight to them. They're super durable. They're easy to move to site, but they have to be pinned. Often pinned every 60 meters or at the ends, if it's less than 60 meters. And if you need less deflection, pinned more frequently. And sometimes it's every 2 units or sometimes it's every unit. And they often use the terms about a standard system, a minimum deflection system, and standard low deflection system and minimum deflection system. And it's really just about the spacing. The more pins, the less it's going to redirect. But there's various, I guess, products there. Obviously, the more you pin it, the more rigid you make it, the less likely it is to contain larger vehicles. And so there is this balance of, it could be the same unit that is MASH TL4 when pinned every 60 meters because there's room for deflection and everything. But that same unit might only be test level 3 when pinned every 6 meters because you've made a very rigid product. And so it's again, that's all in the TCUs, what pin spacings are accepted for the different test levels. Taking both those principles and saying, well, we like the durability of steel, but we want the weight of concrete so that we don't have to pin it, and you get these composite. And there's a couple, Ironman there and Defender Barrier. These do have concrete ballasts inside, which give it the weight, which means that they're trying to provide, a bit more versatility. You could use it freestanding, you could pin it if you need to, and so they're trying to adapt to the market's needs. But composite generally refers to both a steel outer shell and a concrete inside. That does look like concrete a little bit, but that is actually a steel shell, and you can't actually see the concrete ballasts inside. A couple of unique ones. The mobile barrier kind of comes as a big package, a truck that you can drive out to site and protect your road workers. It is being crash tested to test level 3, and you would have a test level 3 TMA on the end. But just to sort of highlight that, the same product approval and assessment process has been gone through with this. Plastic water-filled products. Again, plastic outer shell, they are all filled with water. So they need that weight and mass to redirect a vehicle. As with all the systems, actually, they rely on being connected together. No barrier really works as a single unit or as a single 2 units. It relies on that collective mass to actually redirect a vehicle. It's just the terminals that are generally left empty. And the reason is because when someone impacts the end of it, this can crumple a bit more easily than the rest of the systems. And so generally it's just the first unit and then everything else is filled with water. Most systems do have different colors so that you can tell what is a terminal and what is a longitudinal barrier. The tricky bit is that some systems have identical units. There just happens to be a different color. Whereas other systems do have completely different units. And so the question often comes up, I've run out of terminal units. Can I use a longitudinal product? In theory, for some of the systems, you could just have it empty and it might work. But it's actually, for many systems, that's not the case. There is actually some internal components that are at play. And so I would always recommend getting a terminal unit that's different colored for your plastic end terminal. Bit of a summary there and different containment levels just to highlight concrete. Yep, TL2 to 3, steel TL3 to 4. So you can get pretty big containment when you got the deflection, whereas plastics down in that low category TL1 and 2s. So again, we have these sorts of work sites all over the network. So the need for all 3 different types. Terminals. I'm going to skip through that. Terminals, we do have plastic terminals, freestanding. Some are filled with water, some are empty. They can be installed onto a concrete barrier. They just need the right connection. Generally lower speed though only. And then the other option is crash cushions. So crash cushions can be installed on sort of the pinned products. If you have a steel barrier or a concrete barrier or a hybrid or a composite, then this is going to be rigid, this first unit. Therefore, you might need a crash cushion on that. Now, obviously, in this case, you can see it's a one-way road with a concrete barrier in the middle. In that case, you can get away without much of a transition. It's just the concrete barrier sitting over the top of the, it's the crash cushion sitting in front and sort of overlapping the front of the concrete barrier. However, if there is potential for that reverse impact, if someone could leave the road from the opposite direction and impact this, then that transition is absolutely critical. And a lot of the systems have been tested like that. Your steel barriers have been tested in the reverse direction onto crash cushions. Only one, I think, concrete barrier has. But again, just to highlight, think about, is it accepted only on the approach, or can it be used as a departure terminal as well? Because the testing is different, the risk is different because of that reverse impact. And so you just need to get your combinations right, that you've got your right barrier that can have a terminal on either end. Otherwise, yeah, summary on that, must be correctly connected with all systems. They are pretty complex. Make sure you are using them. Make sure you're designing them per the road authority's requirements, and then make sure you're actually installing them and putting the right bolts where they need to be and connecting them to the foundation in accordance with the manufacturer's manual. Product selection and design, road authority, actual installation and connections and where the post actually goes and fits is down to the sort of manufacturer's manuals. Foundation must be suitable. Again, even with freestanding systems, you need the system to deflect. So the surface does need to be fairly compacted and fairly smooth so that it can actually deflect without snagging and rotating. Similarly, for pin systems, you'll need enough foundation to actually anchor it and make sure that that pin type, whether it's an epoxy or a driven pin, that it actually works and it's long enough for the foundation. So foundation is pretty critical for all temporary barriers, including terminals. Otherwise, minimum lengths, that'll be in the TCU, the deflections and the working widths, that'll be in the TCUs for the different configurations. Obviously, you get less deflection if you pin it more deflection if you pin it less, but also depends on the containment level you need. Otherwise, I think that is it, and I'll either give 5 minutes for the homework and or a couple of last questions.
Yeah, okay. While I bring up something on my screen, Evan, there's a question just around the difference between the straight profile and the F profile concrete barrier, how they would impact performance of a vehicle.
Yep. So they've all been tested. You can contain the vehicle as long as you have enough strength and height. So in theory, the vertical face can contain the vehicle. It just transfers more, I guess, undesirable load onto the occupant. The way the vehicle behaves when it hits a vertical wall is that the vehicle doesn't really lift or it rotates in towards the barrier, and you can create some risks for the driver. Whereas the F shape and the single slope, it's designed to raise the vehicle so that the driver's being sort of lifted away from the barrier, which is actually a much better behavior. We only use vertical face in your really constrained locations and a couple of low speed locations where that behavior isn't as important. But on a highway, you really want to be getting either your F shape or your single slope. So it's not vertical, but it does lift the vehicle the way we want.
Good. All right, thank you. Thanks for that, Evan. I'm just going to quickly run through. So I've sent you an email which has your barrier product, everybody. So and the sheet, but you've really can find it all here in Moodle. I think you should be seeing Moodle there, Evan. Are you seeing Moodle on your screen?
Yep.
Yeah, good. So you go down to module 2. By the way, the recording of module 1's there, and recording of module 2 will come in when it downloads. You're going to do your quiz, but then you go to this Know Your Barrier product. This is your assignment, and you'll click on that. It'll take you into here. You've got a PDF, which is your name and a corresponding product, we would like them in by the 8th if you can. If you're really struggling to do that, let me know and we can work something out. But you find that product, whatever it is, and you download the Word document. And the Word document simply has some areas in yellow for you to fill out. Put in your name, put in your jurisdiction. So New South Wales, Victoria. Insert that barrier product name that you found on the sheet, and then tell us what is its current status in your jurisdiction. Accepted, conditionally accepted, discontinued, legacy. What is the test level of the system? And then give us between 1 and 3 advantages of that system compared to like systems or comparable things. If it's an N terminal, other N terminals. And 1 to 3 disadvantages. And so these are the kind of things you'll be finding in the TCUs and maybe comparing it with other TCUs of similar products. So hopefully it won't take you too long. I think it's fairly obvious. It's in your email, it's on your memory stick, it's in Moodle. So you've got lots of stuff there, and get in contact if you're struggling at all. And I'm happy to talk you through it. Thanks again, Evan, for your wonderful presentations. Evan's contact details are on the slides and on the first set of slides as well. And of course, I can put you in contact if you had any specific follow-up questions. But thank you very much, and looking forward to seeing you all. We're going to have some trivia 3 minutes before we start again on Tuesday next week. Have a good weekend. Do the assignment. It shouldn't take you more than about 15 minutes. If it's taking if it's taking much longer than that, you're probably overcooking it. So get in contact with me, and I'll steer you in the right direction. But have a wonderful weekend, everybody. Thanks again, Evan, and see you on Tuesday.
All right.